So in the previous lecture, we were carrying out the induction step for theorem 122. And let me remind you where we were. We had already proven one direction of it, and we were still needing to prove this direction. So our remaining goal was to prove that for any natural numbers n and m, if there's an injection from n to m, then n is less than or equal to m. The full theorem 122 was an if and only if, but we already proved the other direction. So all that remains is this direction, and this direction we plan to do by induction. We had completed the base case, and we were on the induction step. And if you'll remember from last time, we had kind of a complicated way of writing what it was we were proving by induction. Or not a complicated way of writing it, it is complicated. The thing we're proving by induction is a big for all n statement. So the induction is on m, the base case has m being set to 0 with the for all there, and the induction step also has the for all n, for all natural numbers n, built in there. So here's our induction hypothesis. We're assuming that this holds for a particular m that we have fixed. And now we are going to prove this, that the same thing holds but with m plus 1 instead. So I think I've given this advice before. When you're doing an induction step, you should always be thinking about, especially if you ever get stuck in it, but even when you're not stuck, you should probably always be thinking about how am I going to use the induction hypothesis? So that's what drives the induction step, right? There's got to be some way to use the induction hypothesis. Otherwise, why are you doing the induction? So here, our induction hypothesis is a for all n statement. How do we use that? Well, it's a universal. To use it, you would use universal instantiation, right? That's our fancy name for just applying the for all to a particular case. So there's got to be somewhere a particular natural number n where we have an injection from that natural number to m, and we'll be able to conclude that n is less than or equal to m from this induction hypothesis. All right, so just keep that kind of in the back of your mind, that we have this power, we have this ability to turn injections into m into inequality statements like this. No matter what natural number the injection is coming from. So this is a for all. No matter what natural number the injection is coming from, we have the ability, the power to turn it into a less than or equal to m statement anytime we want. But it works specifically for m. We're trying to show that we can do it for m plus 1. So to prove this universal, I need to do universal generalization, right? So then consider any natural number n, and then our goal becomes to prove this. So goal, well, how about I just go ahead and start with proving the goal. It's an implication, so assume this side. Assume that there exists an injection from n to m plus 1. And then our goal is to prove that n is less than or equal to m plus 1. Okay, great. Now, how do I use what I have here? There exists an injection. Existential instantiation, right? If there exists an injection, then I can get one, give it a name. So get an injection f from n to m plus 1. Now I think it's time to draw a picture to try to decide what to do next with this f. Because our original plan from last time involved, let me show you the picture from last time, a sort of box. So this is after lots of modifications, but we had a black box or a blue box that represents f, which is some unknown way of mapping things from the left side to the things on the right side. And then we had to carry out some rewirings inside of that box to run our argument back then. So this is, and what we were doing was trying to reduce the existence of an injection from 5 to 3 to the existence of an injection from 4 to 2. And that will reduce us, hopefully, to a situation where we can apply our induction hypothesis. So, yeah, you see how that's helpful here? Like, we have an injection from n to m plus 1. If we had an injection from n to m, then the induction hypothesis would apply, right? Because it says if you have an injection n to m, then you get this. So right now we have an injection n to m plus 1, and our goal is try to turn it into an injection n to m. Okay, so let's draw a picture. So n, let's draw n on the left side. So n consists of, let me not put dots, just the names of the elements, 0, 1, etc., all the way up to, dare I call it, n minus 1. And m plus 1 consists of 0, 1, etc., all the way up to m, right? So these are the elements of the set m plus 1, and these are the elements of the set n. And I'm putting n minus 1 in scare quotes because we have not actually defined a minus operation in this course. But let's just go with it for the picture, for the sake of the picture. The picture is not going to be actually part of the proof. It's just supposed to help us come up with the proof. So as long as I don't write undefined things in the proof, that's okay. All right, so here's the set n, and here's the set m plus 1. And make some space. I've got this kind of unknown machine with unknown internals called f, and I know that it applies to each of these, so it's going to take in an arrow from each of these, right? And I don't know that it's surjective, so there's not necessarily an arrow going to each of these over here, but I know it's injective. It's an injection. So in my picture, each of these should receive at most 1 arrow. Nobody should receive 2 arrows like this, right? So at most 1 arrow. So there could be 1 arrow or 0 arrows for each one of them. How about I depict that with a dotted line? So there could be an arrow here or not. There could be an arrow here or not. There could be an arrow here or not. So none of these has 2 or more arrows. Each one has at most 1 arrow, possibly 0 arrows. So that's the picture as it stands. And we don't know how things are getting tangled up inside, right? Like a 0 could get sent to 357, 1 could get sent to 208, like all kinds of weird things could happen, right? So we just don't know what's going on inside here. Well, there's one interesting possibility that would make things a lot easier for us, which is if there is no arrow here, right? Each of these dotted lines represents that there could be an arrow or not be an arrow there. So 1 or 0 arrows there. There could be 0 arrows here, so no arrow going to m. And, you know, just arrows possibly up to scare quotes m minus 1, you know? So what about that possibility? In that case, when that happens, things are really easy because we actually don't need to make much of a modification. We can just go ahead and section off this part of the picture, excluding this thing that doesn't even have an arrow to it anyway. And then that should be a situation that I've sectioned off. That should be a situation to which my induction hypothesis applies. Because, you know, if I collect 0 up through m minus 1 here, then this is m. That set is m, right? Then I have an injection from n to m. And so n is less than or equal to m. And so n is less than or equal to m plus 1. So that's an easy case. If there's not even an arrow there, then, you I can always shrink the codomain down so that it's a more tight set that more tightly contains the range. So what I'm getting at is that we should do a case split between the possibility that M is actually does have an arrow or doesn't have an arrow. Having an arrow means being in the range of the function, right? So either M is in the range or it's not. So let's do a case split based on that. So case 1, the easy one that I just described, is that M is not in the range. There's no arrow there. Then I think I can get that F maps N to M. So what does it take to verify that F maps N to M? Right, do you see why I'm saying this? Because if I take the set consisting of 0, 1, 2, 3, etc. up to M, and then exclude M, then that should be the set 0 up through M minus 1, which is the set called M. So what is needed to prove this? That now F maps N to M. Well, remember, this always says 3 things. The mapping notation says 3 things. You've got a function, I already know that. The domain is N, I already knew that. And the range is a subset of M. So that's what we need to prove. All I know from here is that the range is a subset of M plus 1. So now we claim, so the goal is to get to this, but I don't have this yet. We claim that the range of F is a subset of M. We claim that. So to prove this claim, consider any element of the range of F. Let's call it L. Consider any L in the range of F. Then L is in M plus 1. Since F maps N to M plus 1, the range of F is a subset of M plus 1, right? And L is not equal to M, since M is not in the range of F. So L is in M plus 1, delete M, right? And that should just be M. I think we have a result like that somewhere. Yeah, right here, exercise 122. I think some of you guys did this for your presentation. Yeah, this is expressed in terms of next. So now we know how to write this next M as M plus 1. So if N is M plus 1 here, then you've got M plus 1 here. M plus 1 delete singleton M is M. So by exercise 122, this is M. So L is in M. So that proves, we took an arbitrary L in there and we proved that it's an M. So that proves this inclusion. So new paragraph. Thus, the range of F is a subset of M, and F maps N to M. Now, since F is injective, we have proven that, let me write that a little better, we have proven that N can be injected into M, right? Okay, great. Now we can use our induction hypothesis. Thus, N is less than or equal to M. And is that what we wanted in the end? Not quite. We wanted N is less than or equal to M plus 1, but we're almost there, right? Since m is less than or equal to m plus 1, we have n is less than or equal to m plus 1. Okay, so that's using transitivity, and this is coming from, well, you have many options for that one. You could view it as coming from here, variable 96.1, or also now you can view it as a special case of this, that things are always less than or equal to themselves plus a natural number. So that proves the induction step. That finishes the induction step in case 1, this sort of, I would say, easier case where m is not in the range of f, where you don't have an arrow going to here, so you can just look at this smaller picture here without any crazy modifications. So thus, the induction step is done.